Give a shout out. Emma.
Hello.
Emma's here in class today, even though Hawkeyes lost. Embarrassed on Saturday night, primetime football. But she's got star quality, persistence, and toughness and grit. So she's here to learn about calculus, specifically the formal definition of the derivative as a function. We learned about the formal definition of the derivative at a point. Now it's a function. Namely, that f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. I think so. And, yep, recording. So you guys have seen this before. What's different about this compared to what we've seen before? It's not a, it's x. So instead of just at a point, it's an entire function. Maybe you remember the last example we said was we had a position function of like, say, 5t squared minus t plus 2, and we came up with a velocity function of like 10t minus 1. So this is actually the derivative. So we've seen it already, and we're gonna lay it out for you now. So prime means derivative. Whenever you see this, this is what we do in order to come up with the derivative. There's other operators that imply derivative. So one would be f prime of x. Another one would be y prime. So if you see y prime, that means find the derivative with respect to y. There's different notation. Here's a derivative of y with respect to x. If you see that, it means derivative. Or the derivative with respect to x. You might just see a big old D with an x at the bottom there. Okay? Derivative with respect to x. There we go. Okay? We all good? All right. So, use the graph of f of x to the left, it should say. We've got f of x right here, and we're going to put f prime of x over here. To make a table of values for f prime, then sketch the graph. So I'm going to look specifically where this graph has derivatives equal to 0. So for a value of x equals negative 3, the derivative is 0. Is there another spot where the graph has a derivative of 0? Yep, sure, 2. What else? Yep, 0. So those are important spots on the graph. Okay. Callie, you got a question? You okay? All right. So what about before negative 3? What's the slope before negative 3? Yeah, it's negative before negative 3. What's the slope between negative 3 and 0? It's positive. What's the slope between 0 and 2? And then positive after that. So I'm going to take these and plot these values to show what the derivative of that graph looks like. I'll plot negative 3, 0. Plot 0, 0. And I'll plot 2, 0. If I want to show that the graph is negative, what does it mean for a graph to be negative? Does it mean it's going down or it is below the x-axis? Which one? So I understand what you guys are saying. You're saying that if you have this kind of a graph, that's a negative cubic graph, correct? Okay, but at this point, okay, you may say the graph is headed down, but is the graph positive at this spot or is the graph negative at this spot? It's positive because it sits above the x-axis. So when we're saying that the derivative is negative, that means that the derivative graph will sit below the x-axis. Between negative 3 and 0, it is positive, so it sits above the x-axis. And then between 0 and 2, it is negative, so it sits below. And then afterwards, it is positive. Anybody notice something interesting about the graph? What degree? Okay, so this is cubic, this is quartic. When you take the derivative, it reduces the degree of the function by 1 every time. Second of all, something that's interesting is that, is this a positive x to the fourth or a negative x to the fourth? It's a positive x to the fourth. And this is a positive x cubed, right? Okay. So we're going to use some of those pieces as we move forward, okay? In order for a function to be differentiable at a point A, let's, instead of talking about in order to satisfy differentiability, let's talk about where it fails. We'll talk about that point later. But three classic examples where a function is not differentiable. So, you know, we looked at some pretty easy graph here where we were able to sketch the derivative. What if we ran into some trouble points? Well, these spots would cause trouble for us. So what if I had a graph that looked like this? It's not differentiable at x equals 1, okay? Anybody want to guess why it's not differentiable at x equals 1? What's undefined? Okay. Differentiable means I can take the derivative. For example, right here the derivative is negative. It's discontinuous, right? I mean, the function actually doesn't have any value at 1. It's specifically discontinuous at that spot. We can't take the derivative. Okay? So it's not differentiable at x equals 1 because it is discontinuous. I'll draw another example of a function that's not differentiable at 1 because it's discontinuous. So while the limit exists, you can't take the derivative at a point if the point does not exist as part of the domain of the function. Okay. Another example. This is not differentiable at x equals 1 either. Anybody want to make a guess as to why? If I were to draw a line tangent, what should the tangent line look like that? Or should the tangent line look like that? Or should it look like that? Or should it look like that? Like, how should it look? You really should only have one, right? So here's the issue. As I look at the left-hand side, what's the slope here? What's the slope here? Yeah, -1, +1. The slope from the left needs to be the slope from the right. So this fails here because the derivative from the left does not equal the derivative from the right. And we have one last example where a function might not be differentiable, or I should say instead of might, it in fact is not differentiable. Something like that. That one also is not differentiable at x equals 1. because the tangent line would be vertical, and the slope of a vertical line is undefined. So it's not differentiable at x equals 1 because the tangent line is vertical. So these three situations, we kind of classify them. Instead of writing all this out, we have really three distinct situations. Number one, we have discontinuity. So if it's discontinuous, it will not be differentiable. You won't be able to take the derivative at that spot. The second time you can't take a derivative is if you have a corner. Now, a corner is a common phrase that comes up in calculus, but what it really means is that the derivative from the left is not the same as the derivative from the right. And the final one, and the one that people forget most often, is the vertical tangent. These are your three situations that exist where you lose differentiability. Okay, flip it on over, and let's look at these, okay? We've got some interesting looking graphs here. And what we want to do is we want to identify where the derivative is positive. We want to identify where the derivative is negative. And we also want to identify where the derivative is equal to 0. So let's set up some pieces there to be able to figure this out. Let's do the easy one first, okay? Let's set up where this derivative is equal to 0. So f prime of x is equal to 0 for x equals, where is the derivative equal to 0 for this graph? Yeah, 1. And that's the only spot, okay? Let's look at where f prime of x does not exist. For which values can you not take a derivative? X equals -2. Why? It's discontinuous. So you gave an example of why it's discontinuous, which was great, but it is just discontinuous. What's another spot? K2, why? Yeah, it's discontinuous as well at 2. Yeah, -1, why -1? Yeah, we could call that a corner. Why 0? Vertical tangent. Yep. So those are all situations where the derivative does not exist. You can't take the derivative at those spots. So let's look at intervals where then the derivative is positive. Is the derivative positive or negative here? Definitely negative. So from negative infinity to -2, the derivative is negative. How about after that, from -2 to -1? How about from -1 to 1? Now, because you cannot take the derivative at 0, I have to break it up there as well. So it's negative from -1 to 0, union with 0 to 1. Go get some brain food, come back smarter. Okay, let's finish this off. The interval from 0 to 1 is negative as well. How about the interval from 1 to 2? Positive. And then the interval from 2 to infinity would be, yeah. So we should be able to look at a graph and identify where it's increasing and decreasing, or where the derivative is, I'm sorry, increasing and decreasing is not something that we've technically talked about yet, but where the derivative is positive, where the derivative is negative, and where the derivative is 0 and where it does not exist. So negative is going to be where it's on its way down. So just note that I do have to break up the 0, because at 0 the derivative does not exist, so I can't include it in my interval. Question? Well, it's negative and then it's positive. See that? We good? Okay. All right. So now this is what you're going to be doing for your assignment today. So let's practice this skill. A lot of people get confused with this, so if you have questions, please ask. It says, sketch the graph of the derivative of each of the following functions. So I'm going to look right here. I'm going to say that the derivative is equal to 0 right here. Everybody agree? So I'll plot 0 right there. I'm going to say the derivative is equal to 0 at 0. I'm going to say the derivative is equal to 0 at about 3. So how about between these spots? Derivative positive or negative? Positive. Oh, here. Here. Good. So that means I need to be above, below, above, below. So that's a, go ahead. Good question. That's challenging to think about, but we'll do the square root function because I'm really glad that you brought it up. Okay, so here's my square root function. Okay, agreed? All right. Now, this is going to be hard to think about, but I'm going to redraw it and I'm going to exaggerate it a little bit, okay? Okay, so I try to exaggerate a little bit so we can understand. What would you say about the slope here? Right there. Positive. And it's really positive, isn't it? How about here? How about here? It's slowly leveling off, right? Like the derivative is here is positive, but it's closer to 0, isn't it? So I'm going to be close to the x-axis. And then here, it's really positive. Can I take the derivative at a corner, an endpoint? No, so... Okay, okay. Aaliyah, thank you for bringing it up. Right here. Is the slope of the square root function positive or negative right here? Positive. And it's really positive, right? So the value of the derivative is really positive. Is the slope of the square root function positive or negative here? But barely positive, right? Barely positive. It's not easy to think about. It's going to take a while to wrestle with, but let's try a few examples, okay? That whole degree of one thing, that's harder to understand. Really, with polynomials, we would subtract off the degree. But what about y equals sine of x? You know, what would happen to the power there? Well, it doesn't change power really, but we do look at the derivatives there. So, okay. All right, let's look at this one right here. Okay. Is there any spot where the derivative is equal to 0? Is there a spot where the derivative does not exist? Anytime you have a spot where the derivative does not exist, you have to make sure you have an open circle then, or an asymptote. Something has to happen, okay? How would you describe the derivative here? It's definitely negative, right? Okay, so the slope is negative. How about here? The slope is... Now, the slope is always the same value here, isn't it? Like whatever it is here, it's the same here. So how would you describe the slope here? Approximate it. What would you say? Negative a half? So it's always negative 1/2. And then over here, it's the red graph tells us the slope. So if I point to this spot on the graph, what's the slope? And the red graph says I have a value of negative 1/2. What's the slope here? Negative 1/2. The graph has a value of negative 1/2. Here, the slope is positive 1/2. The graph has a value of positive 1/2. The derivative tells us the value of the slope. See if it comes together for you here. This should be an aha moment. What is the slope of that graph? Approximate it. It's always positive, and you would estimate it to be 1/2. So therefore, it is always 1/2. Doesn't matter what spot on the graph you are on. It will always, thank you, I practice, of a slope of 1/2. Well, thank you. Challenge accepted. Look at that. Boom. All right. Okay. Jill, stop laughing. All right. Okay. She just mocks you. It just days feel like she's ready to just mock you. I don't know. It's hard to trust Jill. You know what I mean? Hard to trust Jill. All right. All right. So how about this one? Okay. Let's think real critically about it. Let's not try to draw it quickly. Let's kind of go little by little here. Slope here. How would you describe this slope? Hey there, bud. Positive, but really close to 0, right? So I'll just write 0 positive because it's really close to 0. How about the slope here? Positive. Slope here? Sure, double positive. But then the slope here, 0. No. No negative positive. Jeez. You're like, how do I teach this? How do I teach? All right, we'll just push through. All right, so the slope is definitely 0 at that spot, right? And then as you move over here, and notice if it's gonna go from really positive to 0, it's got to get less positive in between, right? You can see, as the curve starts to make its way to 0, it's gonna become less positive. It'll be negative, then maybe a lot more negative. Again, negative. But by the time we get out here, it will be, 0, but it will be negative still, right? So if it's 0 and it's positive, what that means is that it's close to the x-axis, but it's right above the x-axis. So we're going to start right above the x-axis. By the time we get to here, we have to be at 0. By the time we get to here, we have to be negative, which is just below the x-axis. So this is kind of what we're looking at right now. And in the middle, we get really positive, and over here, we get really negative. So it looks like the graph is going to look something like that. Oh, very good question. So Emma is asking, how do we know how high to draw it? We really don't. We're just making an accurate guess. So accurate guess. We're making an estimation here. So suppose Emma decided to draw it like this instead. Full credit for the blue one or the red one. The fact is that it gets more positive right at this spot, and it gets more negative right at that spot. And it does hit 0 right there. And it's negative on this side, it's positive on this side. Okay? All right. Let's try an easier one. Okay, so what is the slope of that line? Is it ever not 0? Sweet. No, it's not that bad. Let's just start with the easy part. Is there any spot where you can't take the derivative? Yeah, very good. So like 1.5 or whatever that spot is. So the derivative does not exist at that spot. Why? Because the function is discontinuous. Thank you. So these are the types of phrases that we want to use. It's so nice to be in math class when you hear those words. Discontinuous. Okay. All right. Any spot where the derivative is equal to 0. Yeah, -2 and -1/2, +1/2. So those are spots where it's equal to 0. How about to the left of this spot? Derivative is positive. How about in between these two? Still positive, so it doesn't switch from positive to negative. It goes positive, positive. And then how about between these two? Negative. And then how about after this, between the asymptotes? Positive. Yeah, and it looks like it's going to get super positive, right? So, looks like, how do I show positive to positive with my graph? The graph is positive. Yep, it'll bounce. Exactly. So, yeah, it always stays positive, except at that one spot, the derivative is 0. So that's why the graph comes out and just touches 0 at one spot. And then you can see it gets super positive here, so it heads up towards infinity. Okay? All right, let's look at this last part here. It's a really icky-looking graph. That's all I could find online, so that's what I grabbed. But let's describe this. How would you describe the slope right here? Very negative. Yep, that's a common mistake as people look at it like super positive because you're moving from right to left. We must make sure we move from left to right. As we move left to right, super negative. So that means I'm going to have a value down here. How would you describe the slope right here? Close to 0, but negative. So therefore I sit below the x-axis. So, right, and you get it. In order to try to make sure you don't make the mistake on the test, don't hesitate to draw that tangent line. And you're more likely to say, okay, it is definitely negative, but close to 0. So you can see that that's going to kind of be my graph there. So I would say that green graph is an excellent representation of what the derivative would be. Okay. And so you have a worksheet today, front and back. You really want to make sure that you check the answers. And when you check the answers, please pay careful attention to the open and closed circles. Question. I'll show you.